James Edward Hansen is an American adjunct professor in the Department of Earth and Environmental Sciences at Columbia University. He is best known for his research in climatology, his 1988 congressional testimony on climate change that helped raise broad awareness of global warming, and his advocacy of action to avoid dangerous climate change. In recent years he has become a climate activist to mitigate the effects of climate change, on a few occasions leading to his arrest. In 2000, Hansen advanced an alternative view of global warming, arguing that the 0.74 plus or minus 0.18 degrees Celsius rise in average global temperatures over the previous 100 years had been driven mainly by greenhouse gases other than carbon dioxide, such as methane. However, even then he supported limiting CO2 emissions because the future balance of forcings is likely to shift toward dominance of CO2 over aerosols. Early life and education. Hansen was born in Denison, Iowa to James Ivan Hansen and Gladys Ray Hansen. He was trained in physics and astronomy in the space science program of James Van Allen at the University of Iowa. He obtained a B.A. in physics and mathematics with highest distinction in 1963, an M.S. in astronomy in 1965 and a Ph.D. in physics in 1967, all 3 degrees from the University of Iowa. He participated in the NASA graduate traineeship from 1962 to 1966 and, at the same time, between 1965 and 1966, he was a visiting student at the Institute of Astrophysics at the University of Kyoto and in the Department of Astronomy at the University of Tokyo. Hansen then began work at the Goddard Institute for Space Studies in 1967. Career. After graduate school, Hansen continued his work with radiative transfer models, attempting to understand the Venusian atmosphere. Later he applied and refined these models to understand the Earth's atmosphere, in particular, the effects that aerosols and trace gases have on Earth's climate. Hansen's development and use of global climate models has contributed to the further understanding of the Earth's climate. In 2009, his first book, Storms of My Children, was published. In 2012 he presented a 2012 TED Talk, Why I Must Speak Out About Climate Change. From 1981 to 2013, he was the head of the NASA Goddard Institute for Space Studies in New York City, a part of the Goddard Space Flight Center in Greenbelt, Maryland. As of 2014, Hansen directs the program on climate science, awareness and solutions at Columbia University's Earth Institute. The program is working to continue to connect the dots from advancing basic climate science to promoting public awareness to advocating policy, actions, research and publications. As a college student at the University of Iowa, Hansen was attracted to science and the research done by James Van Allen's space science program in the physics and astronomy department. A decade later, his focus shifted to planetary research that involved trying to understand the climate change on Earth that will result from anthropogenic changes of the atmospheric composition. Hansen has stated that one of his research interests is radiative transfer in planetary atmospheres, especially the interpretation of remote sensing of the Earth's atmosphere and surface from satellites. Because of the ability of satellites to monitor the entire globe, they may be one of the most effective ways to monitor and study global change. His other interests include the development of global circulation models to help understand the observed climate trends, and diagnosing human impacts on climate. studies of Venus in the late 1960s and early 1970s. Following his Ph.D. dissertation, Hansen published several papers on the planet Venus. Venus has a high brightness temperature in the radio frequencies compared to the infrared. Hansen proposed that the hot surface was the result of aerosols trapping the internal energy of the planet. More recent studies have suggested that several billion years ago, Venus's atmosphere was much more like Earth's than it is now, and that there were probably substantial quantities of liquid water on the surface. But a runaway greenhouse effect was caused by the evaporation of that original water, which generated a critical level of greenhouse gases in its atmosphere. Hansen continued his study of Venus by looking at the composition of its clouds. He looked at the near-infrared reflectivity of ice clouds, compared them to observations of Venus, and found that they qualitatively agreed. He also was able to use a radiative transfer model to establish an upper limit to the size of the ice particles if the clouds were actually made of ice. Evidence published in the early 1980s showed that the clouds consist mainly of sulfur dioxide and sulfuric acid droplets. By 1974, the composition of Venus's clouds had not yet been determined, with many scientists proposing a wide variety of compounds, including liquid water and aqueous solutions of ferrous chloride. Hansen and Hovenier used the polarization of sunlight reflected from the planet to establish that the clouds were spherical, and had a refractive index and cloud drop effective radius which eliminated all of the proposed cloud types except sulfuric acid. Kiyoshi Kawabata and Hansen expanded upon this work by looking at the variation of polarization on Venus. They found that the visible clouds are a diffuse haze rather than a thick cloud, confirming the same results obtained from transits across the Sun. The Pioneer Venus project was launched in May 1978 and reached Venus late that same year. Hansen collaborated with Larry Travis and other colleagues in a 1979 Science article that reported on the development and variability of clouds in the ultraviolet spectrum. They conclude that there are at least 3 different cloud materials that contribute to the images: a thin haze layer, sulfuric acid clouds, and an unknown ultraviolet absorber below the sulfuric acid cloud layer. The linear polarization data obtained from the same mission confirmed that the low and mid-level clouds were sulfuric acid with radius of about 1 micrometer. Above the cloud layer was a layer of submicrometer haze. Global temperature analysis. The first GISS global temperature analysis was published in 1981. Hansen and his co-author analyzed the surface air temperature at meteorological stations focusing on the years from 1880 to 1985. Temperatures for stations closer together than 1,000 kilometers were shown to be highly correlated, especially in the mid-latitudes, providing a way to combine the station data to provide accurate long-term variations. They conclude that global mean temperatures can be determined even though meteorological stations are typically in the northern hemisphere and confined to continental regions. Warming in the past century was found to be 0.5 to 0.7 degrees Celsius, with warming similar in both hemispheres. When the analysis was updated in 1988, the 4 warmest years on record were all in the 1980s. The 2 warmest years were 1981 and 1987, with the 1991 eruption of Mount Pinatubo. 1992 saw a cooling in the global temperatures. There was speculation that this would cause the next couple years to be cooler because of the large serial correlation in the global temperatures. Bassett and Lin found the statistical odds of a new temperature record to be small. Hansen countered by saying saying that having insider information shifts the odds to those who know the physics of the climate system, and that whether there is a new temperature record depends upon the particular data set used. The temperature data was updated in 1999 to report that 1998 was the warmest year since the instrumental data began in 1880. They also found that the rate of temperature change was larger than at any time in instrument history, and conclude that the recent El Niño was not totally responsible for the large temperature anomaly in 1998. In spite of this, the United States had seen a smaller degree of warming, and a region in the eastern U.S. and the western Atlantic Ocean had actually cooled slightly. 2001 saw a major update to how the temperature was calculated. It incorporated corrections due to the following reasons: time of observation bias, station history changes, classification of rural-urban station, the urban adjustment based on satellite measurements of night light intensity, and relying more on rural station than urban. Evidence was found of local urban warming in urban, suburban and small-town records. The anomalously high global temperature in 1998 due to El Niño resulted in a brief drop in subsequent years. However, a 2001 Hansen report in the journal Science states that global warming continues, and that the increasing temperatures should stimulate discussions on how to slow global warming. The temperature data was updated in 2006 to report that temperatures are now 0.8 degrees Celsius warmer than a century ago, and conclude that the recent global warming is a real climate change and not an artifact from the urban heat island effect. The regional variation of warming, with more warming in the higher latitudes, is further evidence of warming that is anthropogenic in origin. In 2007, Stephen McIntyre notified GISS that many of the U.S. temperature records from the Historical Climatology Network displayed a discontinuity around the year 2000. NASA corrected the computer code used to process the data and credited McIntyre with pointing out the flaw. Hansen indicated that he felt that several news organizations had overreacted to this mistake. In 2010, Hansen published a paper entitled Global Surface Temperature Change describing current global temperature analysis. Black carbon studies. Hansen has also contributed toward the understanding of black carbon on regional climate. In recent decades, northern China has experienced increased drought, and southern China has received increased summer rain resulting in a larger number of floods. Southern China has had a decrease in temperatures while most of the world has warmed. In a paper with Menon and colleagues, through the use of observations and climate models results, they conclude that the black carbon heats the air, increases convection and precipitation, and leads to larger surface cooling than if the aerosols were sulfates. A year later, Hansen teamed with Makiko Sato to publish a study on black carbon using the global network of AERONET sun photometers. While the location of the AERONET instruments did not represent a global sample, they could still be used to validate global aerosol climatologies. They found that most aerosol climatologies underestimated the amount of black carbon by a factor of at least 2. This corresponds to an increase in the climate forcing of around 1 W per square meter, which they hypothesize is partially offset by the cooling of non-absorbing aerosols. Estimations of trends in black carbon emissions show that there was a rapid increase in the 1880s after the start of the Industrial Revolution, and a leveling off from 1900 to 1950 as environmental laws were enacted. China China and India have recently increased their emissions of black carbon corresponding to the rapid development. The emissions from the United Kingdom were estimated using a network of stations that measured black smoke and sulfur dioxide. They report that atmospheric black carbon concentrations have been decreasing since the beginning of the record in the 1960s, and that the decline was faster than the decline in black carbon-producing fuel use. A 2007 paper used the GISS climate model in an attempt to determine the origin of black carbon in the Arctic. Much of the Arctic aerosol comes from South Asia. Countries such as the United States and Russia have a lower contribution than previously assumed. Anthropogenic impact on climate. The United Nations Framework Convention on Climate Change is an international environmental treaty that has the objective of stabilizing greenhouse gas concentrations in the atmosphere at a level that would prevent dangerous anthropogenic interference with the climate system. In 2003, Hansen wrote a paper called "Can We Defuse the Global Warming Time Bomb?", in which he argued that human-caused forces on the climate are now greater than natural ones, and that this, over a long time period, can cause large climate changes. He further states that a lower limit on dangerous anthropogenic interference is set by the stability of the Greenland and Antarctic ice sheets. His view on actions to mitigate climate change is that halting global warming requires urgent, unprecedented international cooperation, but the needed actions are feasible and have additional benefits for human health, agriculture and the environment. In a 2004 presentation at the University of Iowa, Hansen announced that he was told by high-ranking government officials not to talk about how anthropogenic influence could have a dangerous effect on climate because it's not understood what dangerous means, or how humans are actually affecting climate. He describes this as a Faustian bargain because atmospheric aerosols have health risks and should be reduced, but doing so will effectively increase the warming effects from CO2. Hansen and co-authors propose that the global mean temperature is a good tool to diagnose dangerous anthropogenic interference with the climate system. Two elements are particularly important when discussing dangerous anthropogenic interference: sea level rise and the extinction of species. They describe a business-as-usual scenario, which has greenhouse gases growing at approximately 2% per year, and an alternate scenario, in which greenhouse gases concentrations decline. Under the alternate scenario, sea levels could rise by 1 meter per century, causing problems due to the dense population in coastal areas. But this would be minor compared to the 10-meter increase in sea level under the business-as-usual scenario. Hansen describes the situation with species extinction similarly to that of sea level rise. Assuming the alternate scenario, the situation is not good, but it is much worse for business as usual. The concept of dangerous anthropogenic interference was clarified in a 2007 paper, finding that further warming of 1 degree Celsius would be highly disruptive to humans. An alternate scenario would keep the warming to below this if climate sensitivity were below 3 degrees Celsius for doubled CO2. The conclusion is that CO2 levels above 450 ppm are considered dangerous, but that reduction in non-CO2 greenhouse gases can provide temporary relief from drastic CO2 cuts. Further findings of that Arctic climate change has been forced by non-CO2 constituents as much as by CO2. The 2007 paper cautions that prompt action is needed to slow CO2 growth and to prevent dangerous anthropogenic interference. climate model development and projections. Wilhelm Buechner began the modern development of the general circulation model in the early 20th century. The progress of numerical modeling was slow due to the slow speed of early computers and the lack of adequate observations. It wasn't until the 1950s that the numerical models were getting close to being realistic. Hansen's first contribution to numerical climate models came with the 1974 publication of the GISS model. He and his colleagues claimed that the model was successful in simulating the major features of sea level pressure and 500 MB heights in the North American region. A 1981 science publication by Hansen and a team of scientists at Goddard concluded that carbon dioxide in the atmosphere would lead to warming sooner than previously predicted. They used a one-dimensional radiative convective model that calculates temperature as a function of height. They reported that the results from the 1D model are similar to those of the more complex 3D models, and can simulate basic mechanisms and feedbacks. Hansen predicted that temperatures would rise out of the climate noise by the 1990s, much earlier than predicted by other researchers. He also predicted that it would be difficult to convince politicians and the public to react. By the early 1980s, the computational speed of computers, along with refinements in climate models, allowed longer experiments. The models now included physics beyond the previous equations, such as convection schemes, diurnal changes, and snow depth calculations. The advances in computational efficiency, combined with the added physics, meant the GISS model I could be run for 5 years. It was shown that global climate can be simulated reasonably well with a grid point resolution as coarse as 1,000 kilometers. The first climate prediction computed from a general circulation model that was published by Hansen was in 1988, the same year as his well-known Senate testimony. The second generation of the GISS model was used to estimate the change in mean surface temperature based on a variety of scenarios of future greenhouse gas emissions. Hansen concluded that global warming would be evident within the next few decades, and that it would result in temperatures at least as high as during the Eemian. He argued that, if the temperature rises 0.4 degrees Celsius above the 1950 to 1980 mean for a few years, it is the smoking gun pointing to human-caused global warming. In 2006, Hansen and colleagues compared the observations with the projections made by Hansen in his 1988 testimony before the United States Congress. They described the intermediate scenario as the most likely, and that real-world greenhouse gas forcing has been closest to this scenario. It contained the effects of 3 volcanic eruptions in the 50-year projections, with one in the 1995, whereas the recent Mount Pinatubo eruption was in 1991. They found that the observed warming was similar to 2 of the 3 scenarios. The warming rates of the 2 most modest warming scenarios are nearly the same through the year 2000, and they were unable to provide a precise model assessment. They did note that the agreement between the observations and the intermediate scenario was accidental because the climate sensitivity used was higher than current estimates. A year later, Hansen joined with Rahmstorff and colleagues comparing climate projections with observations. The comparison is done from 1990 through January 2007 against physics-based models that are independent from the observations after 1990. They show that the climate system may be responding faster than the models indicate. Ramstorff and co-authors show concern that sea levels are rising at the high range of the IPCC projections, and that it is due to thermal expansion and not from melting of the Greenland or Antarctic ice sheets. Following the launch of spacecraft capable of determining temperatures, Roy Spencer and John Christie published the first version of the satellite temperature measurements in 1990. Contrary to climate models and surface measurements, the results showed a cooling in the troposphere. However, in 1998, when Schabel determined that orbital decay had an effect on the derived temperatures, Hansen compared the corrected troposphere temperatures with the results of the published GISS model, and concluded that the model is in good agreement with the observations, noting that the satellite temperature data had been the last holdout of global warming denialists, and that the correction of the data would result in a change from discussing whether global warming is occurring to what is the rate of global warming, and what should be done about it. Hansen has continued the development and diagnostics of climate models. For instance, he has helped look at the decadal trends in tropopause height, which could be a useful tool for determining the human fingerprint on climate. As of the 12th of February 2009, the current version of the GISS model is Model E. This version has seen improvements in many areas, including upper-level winds, cloud height, and precipitation. This model still has problems with regions of marine stratocumulus clouds. A later paper showed that the model's main problems are having too weak of a DNSO-like variability and poor sea ice modeling, resulting in too little ice in the southern hemisphere and too much in the northern hemisphere. Climate forcings, feedbacks, and sensitivity. In 2000, Hansen authored a paper called Global Warming in the 21st Century, an alternative scenario in which he presented a more optimistic way of dealing with global warming, focusing on non-CO2 gases and black carbon in the short run, giving more time to make reductions in fossil fuel emissions. He notes that the net warming observed to date is roughly as big as that expected from non-CO2 gases only. This is because CO2 warming is offset by climate cooling aerosols emitted with fossil fuel burning, and because at the time non-CO2 gases, taken together, were responsible for roughly 50% of the anthropogenic greenhouse gas warming. In a 2007 paper, Hansen discussed the potential danger of fast feedback effects causing ice sheet disintegration based on paleoclimate data. George Monbiot reports the IPCC predicts that sea levels could rise by as much as 59 centimeters this century. Hansen's paper argues that the slow melting of ice sheets the panel expects doesn't fit the data. The geological record suggests that ice at the poles does not melt in a gradual and linear fashion, but flips suddenly from one state to another. When temperatures increased to 2 to 3 degrees Celsius above today's level 3.5 million years ago, sea levels rose not by 59 centimeters but by 25 meters. The ice responded immediately to changes in temperature. Hansen stressed the uncertainties around these predictions. It is difficult to predict time of collapse in such a non-linear problem. An ice sheet response time of centuries seems probable, and we cannot rule out large changes on decadal timescales once wide-scale surface melt is underway. Quote, he concludes that present knowledge does not permit accurate specification of the dangerous level of human-made. However, it is much lower than has commonly been assumed. If we have not already passed the dangerous level, the energy infrastructure in place ensures that we will pass it within several decades. In 2013, Hansen authored a paper called Climate Sensitivity, Sea Level and Atmospheric Carbon Dioxide, in which he estimated climate sensitivity to be degree C based on Pleistocene paleoclimate data. The The paper also concluded that burning all fossil fuels would make most of the planet uninhabitable by humans. Analysis of climate change causation. Hansen noted that in determining responsibility for climate change, the effect of greenhouse gas emissions on climate is determined not by current emissions, but by accumulated emissions over the lifetime of greenhouse gases in the atmosphere. By this measure, the UK is still the largest single cause of climate change, followed by the US and Germany, even though its current emissions are surpassed by the People's Republic of China. On public policy, Hansen is critical of what he sees as efforts to mislead the public on the issue of climate change. He points specifically to the Competitive Enterprise Institute's commercials with the tagline, "Carbon dioxide, they call it pollution, we call it life," and politicians who accept money from fossil fuel interests and then describe global warming as a great hoax. Quote, he also says that changes needed to reduce global warming do not require hardship or reduction in the quality of life, but will also produce benefits such as cleaner air and water, and growth of high-tech industries. He was a critic of both the Clinton and George W. Bush administration's stances on climate change. Addressing the potential effects of climate change, Hansen has stated in an interview in January 2009, "We cannot now afford to put off change any longer. We have to get on a new path within this new administration. We have only 4 years left for Obama to set an example to the rest of the world. America must take the lead."